Hi everyone. Today we will discuss continuity and differentiability. So here we can just see if f of x is a continuous function, suppose at x equal to a, f of x is a continuous function at x equal to a. So this does not imply that f dash x means the differentiation of f of x is also continuous. Means if f of x is continuous at x equal to a, f dash x might exist at x equal to a or might not exist. Means that when we say f dash x might exist, means the differentiation of f of x may be possible, it may not be possible. So just that function is continuous, it does not give us the surety that f dash x exists. The differentiation can exist, the differentiability of the function can exist, or it may not exist. So let us take this example to understand this. So if you consider y is equal to suppose f of x, and that is equal to x when x is positive, that is when x is greater than 0, and this is equal to 0 when x equal to 0, is equal to minus of x when x is less than 0. Means the value of this f of x in different interval, it is different. We have f of x equal to x when x is positive, is equal to 0 when x equal to 0, is negative, that is minus of x when x is less than 0. So this function is continuous at x equal to 0 because if you calculate the limiting value of this when x tends to 0 from the right, it means if you calculate the right hand limit, so that exists and that is equal to 0, and the left hand limit when x tends to 0, that is also 0. So left hand limit as well as the right hand limit, that is 0, that exists and that is 0. It means limiting value of y when x tends to 0, the limiting value of y when x tends to 0 and exists and it is equal to 0, because either you consider x tends to 0 plus, you will get this as 0, you consider x tends to 0 minus, you get it at 0, and already it is given that value of this, it is 0 at x equal to 0. So that means the limiting value of this exists, which is also the value at x equal to 0. That means what? The limiting left hand limit exists, right hand limit exists, and if they are equal, and that is equal to the value of the function at that point, so that is condition for what? Continuity of a function. We say that the function f of x is continuous only when the left hand limit, right hand limit, they exist and they are equal, and that limiting value, whether it is left hand or right hand, it is equal to the value of the function at that point. So here, when we are considering the left hand limit as well as the right hand limit when x tends to 0, it exists as well as it is equal to 0, which is the value of the function at x equal to 0. That means the limiting value exists as well as it is equal to value of the function at that point. So this justifies the condition or the prerequisite for continuity of a function. So we can say that it is a continuous function. Now let us consider the differentiability of the function. When we say differentiability of the function, it means the left hand derivative again and the right hand derivative, that should exist and it should be equal. So here if you consider at x is equal to 0, the limit of f of x, because this is the definition for your differentiability of the function, that f dash x is defined like this: f of x plus h minus f of x upon x when this h tends to 0 or x tends to 0. So here we have considered this f of x. So limiting value of f of x plus h minus f of x upon this h when x tends to 0. So either the left hand limit of this as well as the right hand limit of this, if it exists and if they are equal, then only we will say that it is a differentiable function. Now let us see what happens. So here, limiting value of f of x plus h minus f of x upon h is simply limiting value of f of h minus 0 upon h when x tends to 0, because f of 0 it is given as how much? 0. So f of 0 it is 0. F of x plus h, it will be equal to f of h, because we are calculating at x equal to 0. So f of h minus 0 upon this h. Now when h tends to 0 from the right, means that we are calculating the right hand derivative. So when we are considering the right hand derivative, so f of h it is equal to how much? H. This f of h it is equal to h, because you can see here f of x equal to x when x is positive. So we are considering right hand derivative that means x greater than 0, that is x positive. So for that, when x is replaced by h, so that will become h. So f of h, it is equal to h. And this limit is how much? 1. When this is equal to h, so h divided by h, that becomes 1. So right hand derivative here you can say 1. Similarly, if you consider the left hand derivative, that is when h tends to 0 from the left side. I am using the word derivative here because this limiting value of this from the right side or from the left side, that is termed as the right hand derivative or the left hand derivative. That is the definition of the differentiation or the derivative. So when we consider h tends to 0 from the left, that is the left hand limit to consider this left hand derivative. So f of h will be equal to how much? Minus of h. This f of h, that will be minus h, because again, when this x is replaced by h tends to 0 minus. So 0 minus means in this interval, and in this interval, this is how much? Y is minus of x. When that x is replaced by x, so this will become minus of h. So it is equal to minus h. So minus h upon h, that becomes minus of 1. So it is equal to minus of 1. So we can see that the right hand derivative, it is equal to 1. Left hand derivative, it is equal to minus of 1. That means the right hand derivative and the left hand derivative, they are not equal. And when they are not equal, it means the differentiation does not exist. So the function is not differentiable. So it means this function is not differentiable because left hand derivative, right hand derivative, they exist, but they are not equal, which is the required condition for differentiability of a function. So this proves our proposition. This proves the proposition what? That if a function is continuous, it does not mean that it is also differentiable. So this is justified taking this example. So we can again take some more example on this. So now let us see another example. Suppose we have this function f of x is equal to x sine 1 upon x when x is not equal to 0, and f of 0, it is equal to 0. Now as we are aware that sine x lies between what? Minus 1 to plus 1. So we say minus 1 less than equal to sine x less than equal to 1. So here similarly we can see, and this minus 1 less than equal to sine x less than, because this is the standard interval as far as the sine x is concerned. So same thing, you can write this as mod of sine x less than equal to 1. Either you write in this form or you can write in this form. So just using that, we can say mod of sine 1 upon x less than equal to 1 means minus 1 less than equal to sine 1 upon x less than equal to plus 1. So corresponding to this, if it is multiplied by x, so this interval, this will also get multiplied by same x. So here mod of x sine 1 upon x less than equal to x. Now let us consider this. So here if you calculate the limiting value of this, if we calculate the limiting, because for continuity check, we calculate the limiting value. We need to have left hand limit is equal to right hand limit, and it should be equal to the value of the function at that particular point. So this gives us the condition or the required condition for continuity of a function. So let us calculate the limiting value of this. So limit of x sine 1 upon x when h tends to 0, that will be equal to what? 0. So this shows that the function is continuous because the value of the function at x equal to 0, it is also 0. So left hand limit, right hand limit, it is same. It exists, it is same, and that is equal to value of the function at that particular point. So this justifies that the function is continuous function. Now let us check the derivability of the function or differentiability of the function. So if we differentiate this, that is differentiation of x sine 1 upon x with respect to x, that can be represented as limiting value of h sine, this is from the definition of the differentiation, as sine 1 upon x minus 0 upon this h. Now, so this h and this, that will get cancelled. So this is equal to, because x sine 1 upon x, so when x is replaced by s, so that becomes your s sine 1 upon this h, minus of what? F of 0. So f of 0, it is already given as 0, so it is equal to 0, divided by h. So this h and h gets cancelled. So finally we are getting limiting value of this limiting value of sine 1 upon h when this h tends to 0. Now the limiting value of this does not exist. Limiting value of sine 1 upon x when x tends to 0, that does not exist. So it means the limiting value itself does not exist. So there is no question of the differentiability or derivability of the function. So we can say from that that the function is not differentiable at x equal to 0. So again, so function is not differentiable, it is continuous, but it is not differentiable. So this again justifies our proposition that all continuous functions are not derivable function. You can see this. We can now conclude that differentiable functions are continuous. And all differentiable functions are continuous. If a function is differentiable, it means it is continuous. But if a function is continuous, it does not mean that it is differentiable. So here we can just conclude that all differentiable, and every differentiable function is a continuous function, but the converse is not true. Converse is not true. Then the opposite of this, all continuous functions are not differentiable function. So I hope these two examples gives us a clear picture that every differentiable function is continuous function, but continuous functions are not necessarily differentiable function. The condition is for differentiability, the condition is that functions must be continuous. That is the first condition. If a function is continuous, then only we can say that it may be a differentiable function, it may not be a differentiable function. So depending on nature of the function, if the function is continuous, then only either it will be a differentiable function or it may not be a differentiable function. But if a function is a differentiable function, obviously it will be continuous function. So we will see some examples based on this.